Hello everyone, welcome to Dr. Ravi's Academy. In today's virtual class, we'll be solving a problem on resultant of coplanar non-concurrent forces. Here, let us look at the beam, a simply supported beam. It is subjected to a variable load. One end is 60 Newton per meter, two, it is linearly increasing to the other end 180 Newton per meter. And length of the beam is given, that is 12 meters. He is asking you to find out the resultant as well as its magnitude as well as its position of the resultant. So as you know, the standard procedure of determining the resultant of coplanar non-concurrent forces, it is resultant magnitude R and the slope of this particular force and the position of the resultant force. These are the three parameters, and looking at this, you can see that there is no horizontal force in this, so sigma fx will be 0. And whenever you come across with such type of loads, let us divide into this area, total area divide into, I am drawing a horizontal line such that, so this is my rectangle, I am denoting it by 1, and this is a triangle denoting it by 2. So that means a rectangle of size, let us look at this. This height is 60 Newton per meter length, having a length of 12 meters. So this is my rectangular loading, right? And another loading is a triangle. The triangle loading is like this. Height, you can see that it is 180 minus 60, you have 120. So it is, the triangle is having, it is 120 is the height and 12 meters is the base, and it is a right angle triangle. So you have divided this particular loading diagram into two simple diagrams. One is rectangular load. I am calling this as P1, the area of the diagram. I am calling this as P2. So simply the area of the diagram is the load. So let us calculate this P1 value. So P1 is equals to rectangular area, that is 60 into 12. This is 720. It is newtons. 720 newtons. P2 is equals to area of the triangle, half into base into height. Height is 120. Again it is 6, 120. This is also 720 newtons. Both are equal. And the point of application, P1 is exactly the midpoint. It is a rectangular load. This is at a distance. The span is 12 meters and it is at a distance of 6 meters. And the triangular loading is, it is at a distance 2/3 of the length, that is 12. So that means it is 8 meters. It is 8 meters. This is nothing but your 8 meters. 2/3 of, this is a location for the centroid of this point load. So you know the load magnitude and position of that, and the load magnitude of the triangular load and position of that also you know. Now you can calculate what is sigma Fy. So sigma Fy is equals to, here both the loads are equal, it is downwards, it is minus 720 minus 720, and this becomes minus 1440 newtons. So this is your sigma Fy. So once this sigma Fx is 0, your resultant itself is, resultant is equals to sigma Fy is equals to, it is 1440 newtons, which is acting vertically downwards. So theta is, once it is acting vertically downwards, theta means is 90 degrees. So first two values or parameters are determined. Now you have to locate the position of the resultant force. To locate the position of the resultant load, let us apply Varignon's theorem. As you know very well that it is moment of the resultant force, let us say R, about I am taking about point A left hand, is equals to moment of its component forces. Component forces, one is P1 about A and another is P2 about A. So this is Varignon's theorem. So I am applying Varignon's theorem. Varignon's theorem. According to Varignon's theorem, now let us write the moment equation. It is 1440, right? This is the resultant magnitude at a distance d is equals to, it is P1, that is 720. 720 is at a distance of 6 meters, plus again this is also 720 at a distance, it is 2/3 of this 12, that is 8 meters. And of course only d is unknown, and this answer is 7 meters. You are going to get this value as 7 meters. I hope you understood this particular problem. Let us practice it. Thank you for watching this video.